Okay, the water vapors enter a diffuser at a pressure of 0.7 bars and temperature 160 degrees Celsius and velocity 180 meters per second. The inlet to diffuser has an area of 100 centimeters square. During its passage through the diffuser, the fluid velocity is reduced to 60 meters per second. Then pressure increases to 1 bar and 0.6 joules per gram of heat is transferred to the surroundings. Calculate the final temperature, mass flow rate, and the outlet area in centimeter square. So, what all is given to us? Now, we are given that the inlet conditions and outlet conditions. In the inlet conditions, we are given 0.7 bars, 160 degrees Celsius, and 100.7 bars, 160 degrees Celsius, velocity 100 meter per second, and the area is 100 centimeters square. At the outlet, we are given the pressure is reduced to is increased to 1 bar. Velocity is reduced to 60 meters per second. Outlet area we need to find out. Final temperature we need to find out. Also, we need to find out the mass flow rate and the outlet area and final temperature. Also, we are given that 0.6 joules per gram of heat is transferred. 0.6 joules per gram of heat is transferred. So if we make the diagram of this diffuser, this is a nozzle diffuser, which we are drawing here. This is a nozzle diffuser, which we have. And this is the flow of water. What is this? This is a nozzle diffuser. This is the diagram or pictorial representation. Now, for solving this question, we know that the first law of the statement of first law of thermodynamics, according to the first law of thermodynamics, according to the first law of thermodynamics, we have Q plus heat transfer plus shaft work is equals to change in enthalpy plus change in kinetic energy plus change in potential energy. Okay, so now this is given to us as 0.6 joules per second. Shaft work is 0 in case of a nozzle, and also the potential energy is 0 as there is no significant increase or decrease of elevation. So we have that the heat exchanged is equals to change in enthalpy and the change in kinetic energy. Change in kinetic energy can be easily calculated as the velocities are known, and we can calculate the enthalpy values from the pressure values which are given, pressure and temperature values. So if we calculate the change in kinetic energy, it is V2 square minus V1 square divided by 2. V2 square is 60 square minus 100 square divided by 2. So this we get as minus 14.4 kilojoules per kg. Kilojoules, for kilojoules, we have divided it by 1000. Its answer was 1400. So this was which we got on solving this, and dividing it by 1000, we got the actual value as minus 14.4 kilojoules per kg. So this is change in kinetic energy. Next, if we look for the temperature and the enthalpy values, which we require for this. So we are given 0.7 bars inlet condition, 0.7 bars in 160 degrees Celsius. So at 0.7 bars in 160 degrees Celsius, the 0.7 bars, the saturation temperature is 89.96 degrees Celsius. Given temperature is this. So we have the state at the inlet is superheated steam or superheated vapors. So for by the interpolation method, we have at 160 degrees Celsius, the value of enthalpy is 2798.32 kilojoules per kg. So this is the value of H1. Next, we have the value of, next we need to find out the value of H2. For finding out the value of H2, we will be doing that we will be substituting this in that equation. We had written above, according to the first law of heat exchanges, kinetic energy plus change in enthalpy. This is 0.6. Kinetic energy we found out to be minus 14.4, and delta H is H2 minus H1. H1 we know, as this thing. So H2 from here is pressure. Pressure at outlet is 1 bar, enthalpy is 2812.4 kilojoules per kg. The temperature at this enthalpy value, at 1 bar. Now you need to go to your steam tables, superheated steam tables. We will be going there. Now open them and go to the 1 bar option. Okay, 1 bar option in the superheated steam tables. Yeah. So here we have, we get that this much temperature, this much value of enthalpy is at a temperature of 167.987 degrees Celsius. So this is the final temperature which we had to find out. This is the final temperature. Next, we have to find out mass flow rate and outlet area. So for mass flow rate is that your, we know mass flow rate is A1 V1 upon mu1, which also equals to A2 V2 upon mu2. This can also be written as A1 V1 rho 1 is equals to A2 V2 rho 2. This is 100 centimeters square. This is 100 meters per second. The density. Or you can substitute the values in these as well, specific enthalpy, the specific volume values we can find out. Leave this method. It will be very lengthy by this, because density we would be needing to find out. So in this, if we substitute the values of 100 centimeters square into 100 meters per second into the specific volume values at 0.7 bars and 160 degrees Celsius, they are 2.841 meter cube per kg, and this is A2 we need to find out. This is 60 meters per second, and the value of V2 is 2.022 meter cube per kg. So this meter gets cancelled out, and meter square. We need to convert this into centimeters, and then we can convert it to meters. Okay, or you can leave it like this. The value of A2 on calculation from this, it comes out to be 213.49 centimeters square. So it is like this kind of a diffuser, that this area is, inlet area is smaller, outlet area is larger, or it can enter from here as well. Anyway, so this is the question. This is the your outlet area, which we have find out. Okay. So with this, we finish with the question. Also, you have this general observation that in a turbine, Turbine, it is always contributes to shaft work at the expense of enthalpy. And your nozzle. Nozzle contributes to kinetic energy at the expense of enthalpy. Both of them at the expense of enthalpy. This work is done. So with this, we finish with our